Hello students and welcome back to Thermodynamics. In this part of the chapter, we are going to talk about two very important concepts. The first one being internal energy. Now internal energy is normally represented with a capital U, but in some of the books it is also given as capital E, so don't get confused. I am talking about energy possessed by the system by default. I'm talking about kinetic energy of the molecules. I'm talking about potential energy of the gas. So these energies which are possessed by default by the gas, that's called as internal energy. But then again, if you are looking for the textbook definition, we can say that every substance possesses a fixed quantity of energy which depends on its chemical nature and its state of existence, and this is called internal energy. So every substance is associated with some quantity of energy, energies like kinetic energy and potential energy. So these energies together make up internal energy. Now kinetic energy, as we all know, is based on motion. It depends on movement, and there are different types of movements, so there are different types of kinetic energies as well. For example, we have translational motion, which means motion from one point to another point directly through a straight line. That's called as translational motion. We have rotational motion, that means rotation of a substance about its axis, as you can see right next to me. We have vibrational, which is kind of self-explanatory. Okay, so along with that, we also have electronic energy. That is also another form of kinetic energy which deals with movement of electrons. So these are all the different types of kinetic energy possessed by the system. We also have potential energy. Now potential energy may deal with intermolecular interactions. That means from one molecule to another molecule, the attraction that we have, that is called as intermolecular attraction. We may have intramolecular, that means within one molecule, whatever energies are there, that is called as intramolecular energy. We may also have nuclear, which is again kind of self-explanatory. So all these different energies combined make up the internal energy. That is energy by default possessed by the system because it exists in a particular state. Now here there are two very important points that you must know about. First one is that for an ideal gas, the internal energy is a function of the temperature. It depends on the temperature. If the temperature is increased, the molecules will start moving very fast, and if they start moving very fast, the internal energy will also increase. Another thing that we need to know here is that internal energy cannot be measured. However, change in internal energy can be measured. हम internal energy यानी कि U directly measure नहीं कर सकते, because internal energy measure करने के लिए हमें हर एक molecule का vibration, rotation and उसका motion, वो भी किस direction में है, ये सारी चीजें हमको पता करनी होंगी, and currently we do not have sufficient technology to find that out. So internal energy हम find out नहीं कर सकते, लेकिन change in internal energy हम find out कर सकते हैं by using the first law of thermodynamics. Now, there are some things that you must know about internal energy, like it is an extensive property. Now, I have two gases right next to me, and it is obvious that the second gas has got more internal energy because it has got more matter. क्योंकि second gas के पास ज़्यादा matter है, इसीलिए उसमें movements भी ज़्यादा हैं, kinetic energy भी ज़्यादा है, potential energy भी ज़्यादा है. So in short, internal energy is more in the second gas, which means that internal energy depends on the amount of matter. So it's an extensive property. Another thing that you must know is that it's a state function. यानी कि अगर कोई गैस है, उसको आप compression और expansion के cycle go through करवाते हो, something like this. So the gas is at position A, and after undergoing series of changes, it comes back to its original position. So since the gas is back to its original state, original position, same pressure as before, same volume as before, same temperature as before. तो आपने expansion, compression किया, it went away, did all sorts of things, and then it came back to its original state. The internal energy does not change, which means that it does not depend on the path followed, so it is a state function. इसी कॉन्सेप्ट को मैं ये भी कह सकता हूं कि फॉर अ साइक्लिक प्रोसेस डेल्टा यू is zero. Internal energy does not change because after the gas has gone and done all sorts of things and it is back to the original internal energy. So for a cyclic process, delta U is equal to zero. Now one thing that you must remember is that internal energy changes with temperature only for ideal gases. So you can see two illustrations right next to me. In one of them you can see the molecules are moving much faster as compared to the first one, which means that the temperature in the second gas is more. And if the temperature is more, kinetic energy is more, so the internal energy is also more. So internal energy changes only and only with temperature for ideal gases. Again, like I told you before, इंटरनल एनर्जी को हम मेजर नहीं कर सकते क्योंकि हर एक मॉलिक्यूल का काइनेटिक एनर्जी, ट्रांसलेशनल एनर्जी, वाइब्रेशनल एनर्जी, रोटेशनल एनर्जी, हम ये हर एक मॉलिक्यूल का मेजर नहीं कर सकते. सो यू कैन नॉट बी मेजर्ड बट डेल्टा यू कैन बी measured, and because internal energy is a form of energy, it is measured in joules and ergs. So these are some important points related to internal energy that we must know about. Now we have already seen the sign convention in the previous module. We have discussed the sign convention of work and we have discussed the sign convention of energy. Energy में heat आ जाएगा, internal energy आ जाएगा, enthalpy आ जाएगा. So any kind of energy, sign convention remains the same. So for endothermic process, delta U will be positive, and for exothermic process, delta U will be negative. I hope that is clear to all of you. If you have understood the concept of internal energy, let's now move to the concept of the first law of thermodynamics, and here we are finally dealing with the laws of thermodynamics. We can see that we have a person here who is not very energetic. He does not have a lot of energy by default. Let's say that his energy level is 10 joules. Now I know that internal energy cannot be measured, but we are just taking an arbitrary number. सिर्फ assume कर रहे हैं एक arbitrary number यहाँ पे. So let's say that this guy has an internal energy of 10 joules. Well, he's not very happy about the fact that he's not energetic, so he decides to have some food which will give him about 70 joules of energy. So already he had 10 joules of energy, he has consumed 70 more, so now he's shot up to 80 joules by addition of 70 joules of energy by eating food. अब क्योंकि 80 joules पे अब इसके अंदर एनर्जी आ गई है, he is now very energetic, so he decides to go out for running, and in doing so he spends 50 joules away, which means from 80 now he will come down to 30 joules. So initially he was at 10 joules, now he is at 30 joules of energy. After consuming some food and doing some exercise, he is now at 30 joules of energy, which means that now there is a difference of 20 joules if you compare it with the original position. So I can say that this 20 joule is nothing but the change in internal energy, that is delta U. Earlier the internal energy was 10 joules, now it is 30 joules, which means delta U has been plus 20. This is nothing but the algebraic sum of the heat which was absorbed, that is 70 joules, and the work which was done, that was minus 50 joules. Remember, the work was done by this guy, and that's why it is negative in sign convention. So I can say that delta U is Q plus W, Delta U is the change in internal energy. Q is the heat that is absorbed, so it is plus 70, and some work was done by the person here, by the system, so it is minus 50 joules. And this means that energy was neither created nor destroyed. Energy was just transferred from the food to the person and was converted into work. So energy cannot be created, it cannot be destroyed, it can just be converted from one form to another form, and that is the first law of thermodynamics. Energy can neither be created nor be destroyed, it can be converted from one form to the other form. So first law of thermodynamics is technically the law of conservation of energy. We can also say this law by different statements, like the total amount of energy in the universe remains constant because no new energy is being created, no energy is being destroyed, so the total amount of energy in the entirety of the universe will remain constant. We can also say that the energy, the total energy of an isolated system remains constant. An isolated system does not absorb heat, it does not release heat. It is totally isolated. Means there is no exchange of matter, there is no exchange of heat. Here also the total energy will remain constant because no new energy can be created or none of the old energy can be destroyed. We can also say that whenever a given quantity of energy of one kind disappears, then an equivalent amount of energy of some other kind will appear. That means energy will be converted from one form to the other. When one form disappears, equivalent amount of another form appears. That is another statement of the first law of thermodynamics. We can also say that it is not possible for a perpetual motion machine to do work without consuming some form of energy. That means if you do not give energy to a machine, it cannot run perpetually, means continuously, means forever. यानी कि ऐसी कोई मशीन नहीं हो सकती जो हमेशा के लिए चलती रहे without giving energy, because it cannot create energy to run, you will have to give energy. So it is not possible for a machine to work continuously without consuming some form of energy. These are all the different statements of the first law of thermodynamics, और ये सभी आपको याद होने बहुत ही जरूरी हैं. Now mathematically we know that delta U is equal to Q plus W, right? Change in internal energy is nothing but the heat absorbed or released plus the work which is done either by the system or on the system. करेक्ट. अब इसी इक्वेशन को हम अलग अलग तरह के प्रोसेसेस में अप्लाई करेंगे. फॉर एग्जाम्पल, अगर आइसोथर्मल प्रोसेस रहा तो टेम्परेचर चेंज नहीं होगा, एंड इफ द टेम्परेचर डज नॉट चेंज, इफ T remains constant, then delta T is 0. Temperature is constant, so internal energy will also remain constant, that is delta U will also become 0. And if delta U is 0, that means 0 is equal to Q plus W, which means Q is nothing but minus W, or you can also say that W is minus Q. इसका मतलब ये है कि आप जो भी हीट दे रहे हैं वो डायरेक्टली वर्क में कन्वर्ट हो रही है, इंटरनल एनर्जी बढ़ाने में कुछ नहीं जा रहा, बिकॉज टेम्परेचर इज कांस्टेंट, सो इंटरनल एनर्जी इज आल्सो कांस्टेंट, इट विल नॉट चेंज. व्हाटएवर हीट यू गिव टू द सिस्टम will get converted into work. And this is the reason why I had told you when we were doing maximum work, W max, तो आपको याद आया होगा, maximum work happens in isothermal and reversible process. रिवर्सिबल प्रोसेस में वर्क डन क्यों मैक्सिमम होता है ये हमने ग्राफ से स्टडी किया था, लेकिन आइसोथर्मल प्रोसेस में वर्क डन क्यों मैक्सिमम होता है ये हमने अभी देखा, क्योंकि आप जो भी हीट देते हो वो डायरेक्टली वर्क में कन्वर्ट होता है, इंटरनल एनर्जी बढ़ाने के काम नहीं आता, क्योंकि आइसोथर्मल है, इंटरनल एनर्जी विल ऑल्सो नॉट चेंज. इफ वी टेक एन एडियाबैटिक प्रोसेस जिसमें हीट का कोई एक्सचेंज नहीं होता, so we can say that Q is equal to 0, which means delta U is equal to 0 plus Q, जिसको मैं ऐसे भी लिख सकता हूं कि delta U is equal to W. Whatever work is done, it changes the internal energy of the system. ध्यान दीजिएगा यहां पे delta U is equal to W. Whatever work is done, it changes the internal energy of the system, and this is why even if you put hot tea inside a thermos flask, after 1 day or maybe 2 days, that tea will become lukewarm. We can also say that for an isobaric process where the pressure remains constant, okay, अगर pressure constant रहेगा तो ये equation वैसा का वैसा ही रहेगा, ये equation में कोई change नहीं आएगा. We can say that pressure does not change, pressure remains constant. So delta U is equal to QP plus W. Now this equation can also be written as QP is equal to delta U minus W, और हम already जानते हैं work done क्या है, it is nothing but minus P delta V, where P is the external pressure. तो इसको अगर हम ऊपर substitute करें, we can say that QP is equal to delta U plus P delta V. तो equation as such change नहीं हुआ है, बस थोड़ा सा rearrangement हुआ है, but the equation in general remains the same. QP is equal to delta U plus P delta V. Okay, and last but a very important process, that is isochoric process, जहां पर volume remains constant, delta V is 0. अगर volume constant रहेगा तो मैं ये कह सकता हूं कि delta U is QV plus 0, because हम ये बात जानते हैं कि work done in isochoric process is 0. अगर वॉल्यूम कांस्टेंट रहेगी तो कोई वर्क नहीं होगा. ध्यान से देखिए ये इलस्ट्रेशन, जब वॉल्यूम चेंज हो रही है तो वहां पर वर्क हो रहा है, जो हमारा व्हील है इट इज मूविंग, बट जैसे ही वॉल्यूम चेंज होनी बंद हो जाती है, अब आइसोकोरिक प्रोसेस हो गया है, वॉल्यूम इज नॉट चेंजिंग, अब ये पहिया, अब ये व्हील मूव नहीं होगा. So in an isochoric process, no work is done, and because of that, delta U is equal to QV plus 0. In other words, I can say that QV is equal to delta U. जो भी मैं हीट दे रहा हूं सिस्टम में, वर्क में तो कुछ जा नहीं रहा because the volume is not changing. वो पूरा हीट सिर्फ इंटरनल एनर्जी बढ़ाने के काम आएगा. Okay, so we saw what is the first law of thermodynamics, और इस लॉ ऑफ थर्मोडायनेमिक्स को, फर्स्ट लॉ को, हम कैसे अलग अलग प्रोसेसेस में, आइसोथर्मल, एडियाबैटिक, आइसोबारिक, आइसोकोरिक, इन प्रोसेसेस में हम कैसे अप्लाई कर सकते हैं, वी जस्ट सॉ दैट. नाउ बिफोर वी कंक्लूड दिस मॉड्यूल, इट इज इंपॉर्टेंट एक बार हम मॉडिफाइड फॉर्म ऑफ फर्स्ट लॉ ऑफ थर्मोडायनेमिक्स भी देख लेते हैं. दिस मॉडिफाइड फॉर्म ऑफ फर्स्ट लॉ ऑफ थर्मोडायनेमिक्स इज एन एप्लीकेशन ऑफ द थियरी ऑफ रिलेटिविटी. And you know that the theory of relativity was given by the big man himself, that is Albert Einstein. We also know that the equation of the theory of general relativity is E is equal to mc square, where E is the energy, m is mass, and c is the velocity of light, or the velocity of electromagnetic radiation through vacuum. That is 3 into 10 raised to 8 meters per second. Light is really very fast. So we have all these terms, and we know that E is equal to mc square, and there are many implications. But one of the implications of this theory is that energy and mass can be interconvertible in a very weird kind of a way. Now, to explain you how energy and mass are interconvertible, it will require a totally separate module by itself. So right now all you need to understand is that energy and mass can be kind of interconvertible, but this will create problem with the first law of thermodynamics. The first law states that the total energy in the universe should remain constant. But if some energy and some mass are interconvertible, that will create a disbalance in the whole equation. So instead of saying that energy is constant, we can say that the total mass and energy of an isolated system, or the total mass and energy of the universe, will remain constant. Okay, so we have seen in this part of the chapter, we have seen internal energy, we have seen the first law of thermodynamics, and just now we saw the modified form of the first law of thermodynamics. Hope you've all understood this module. In the next part of this chapter, we will study a very important property called enthalpy. So till then, stay tuned, and if you like our videos, do like, comment and share. Thank you.